Again, like I said, all right, so we are looking at a question from the 2023 paper 2. It says hydrogen peroxide, and we have that in the bracket, decomposes to produce oxygen and water in the presence of potassium iodide, a catalyst. The effect of the concentration of the hydrogen peroxide on the rate of reaction was investigated. Now, we should know a little bit about rate of reaction. It is how fast, you know, reactants break down or react to produce products, or how fast products are formed. Can you remind me of some of the things that, some of the factors that affect rate of reaction?
Catalyst,
A catalyst,
surface area,
surface area,
temperature,
temperature,
concentration.
and concentration. Beautiful. And as you would have heard me say, or if you were reading along, we are investigating how concentration would have affected the rate of reaction of hydrogen, the decomposition, which we know we're breaking down, decomposition of hydrogen peroxide. So for each experiment, the concentration of the hydrogen peroxide was changed, and the time taken for the hydrogen peroxide to decompose was measured using a stop clock as shown in figure 1. We're looking at the stopwatches, and we're seeing that each time they're basically changing that concentration of the hydrogen peroxide. Now, I tell my students that, and let me see if I can increase. When you're working with these, what you can do is to get your ruler, right? And you can place it to indicate the exact value of the scale that is presented to you. So you can help me out right here. Help me out, help me out. In the first experiment,
59 seconds.
second, in the second experiment,
42 seconds.
third,
31 seconds.
fourth,
25 seconds.
fifth.
21 seconds.
All right, as usual, I normally say just, well, some persons would have had the past paper booklet working with, so you can be going along as we work. You have the book in front of you, or you can write down the values. So yeah, those are the time taken. So we continue. For the first question, it says define the term rate of reaction, 1 mark. So anybody wants to go? Let's go, let's go. Anybody? What is rate of reaction?
Time it takes for the reactants to react fully.
So we're just using what the time is the time the reactants take, and we can say to form products. Yeah. So remember, once we see that word rate, we're referring to how fast the time. So it is how fast the reactants are used to create products, whichever way or how fast products are created from reactants, whichever way you want to construct your sentence, 1 mark. Find the term catalyst. And for persons who do the bio as well, we would have seen there, this is not a new term. It's the same. What when we talk about catalyst in bio, what comes to mind?
The enzymes,
Beautiful. And what are enzymes? What do enzymes do?
they speed up a reaction in the
Wonderful.
body.
So they do this by lowering the activation energy. Remember, one of the things that we talk about in terms of a reaction, we have that collision theory, where in order for a reaction to occur, we must have particles colliding. We must have particles colliding at a specific orientation. We must have them colliding with a certain amount of energy. So that energy is known as the activation energy. And what catalysts do is to reduce the amount of activation energy. And I think I mentioned this before. That's one of the reasons why we introduced the catalyst. Um, it is, you can look at it as a positive way in terms of green chemistry, where we say that less energy is utilized when we utilize a catalyst. So we're making it more environmentally friendly, so that we don't have to maybe burn in a particular case like fossil fuel. Like for example, when we were talking about the cracking of organic, the hydrocarbons last week, once you have a catalyst present, then the amount of energy that is needed would have been reduced. So catalyst helps to speed up the reaction by lowering the activation energy, and that's the energy needed or required for the reactants to have when they collide. Yeah? So concentration, we have this table, and what they would have been, um let me go back, sorry. So for each of the experiments shown on the stop clocks in figure 1 on page 4, record in table 1 the time taken for the hydrogen peroxide to decompose. And we said that hydrogen peroxide decomposes into what? How are them there? What the hydrogen peroxide break down into?
Oxygen and water.
Thank you so much. And so, sorry, the effect of the concentration of hydrogen peroxide on the rate of reaction, we want to keep that in the back of our heads. Not only that, you have been, and I just want to include this, if you recognize, this would have been the first question. Usually I do this. So let me go back to it to mention it. For this it says, very important, do not spend more than 30 minutes on question 1. You see, this is a lab-based question and it's very lengthy in terms of what is required. But at the same time, to get a better and an overview in terms of trying to acquire a certain number of marks, you are required to not spend more than 30 minutes. So if you're in the exam and you're on question one is usually a lab-based question. Question one usually involves you creating a graph. So the persons who are weak in that area, remember to practice your graph, how to find your scale and to plot your points. Very critical because the first question you'll do will require you to do that. Now, if you reach time yourself, have a watch. Remember, you won't be able to have your phone, so just walk with a watch, not a smart watch, regular watch, and you time yourself. So if you recognize, normally they also have clocks in the room. So if you recognize that you're beyond the 30 minutes, you just stop and go to our next question so that you can maximize the marks. I just wanted to include that for those who, you know, maybe have not heard that going into the exam for a first time. I know some persons might be grade 10s and they did exams in grade 10. Now, so the experiment, what was the time in second for the first one? Could you remind me?
59.
So 59. The second experiment,
42.
third,
31.
fourth,
25.
fifth.
21.
All right. And so we would have when we talk about this, let's look at this concentration of hydrogen peroxide, and we look at this in terms of moles per dm cube. Remember, we can represent concentration, and once I tell my students, once you hear concentration, it's really telling you how much is in 1000 centimeter cube or 1 dm cube. Now you have two ways in which we can quantify concentration. We can go moles concentration or mass concentration. So if it is moles concentration, what this is saying, 0.10 moles of hydrogen peroxide is in 1 dm cube or 1000 centimeter cube, right? And when we look at this, what is happening to the concentration? What is happening to the concentration, guys? When we look at from experiment 1 to 5.
So it's increasing.
So it's increasing. Beautiful. And the thing about it, we don't only just go in and I don't just only just come and just give you an answer. I use it as a means of teaching as well. So if it is increasing, what does that mean for the rate of reaction? How will that affect the rate of reaction?
Rate of reaction will also increase.
The rate of reaction will also increase. Beautiful. Now, can anybody tell me why the rate of reaction will also increase?
Because When the concentration is higher, it takes less time for the reactants to get used up for
Uh,
the
Wonderful, true. But why would it take less time? I'm still searching for something. What about increasing the concentration allows for an increase in rate of reaction?
sure, it increases the collision frequency of the particles. So they're
Beautiful.
more likely.
Who that? So we recognize and we know that how often the particles collide. Because remember, we know in order for the reaction to happen, particles must collide. So if you have more particles in whatever system that you're doing this reaction, then of course you're going to have more collision happening. And so that is how concentration really allows for an increase in the rate of reaction. So if I only had 5 particles, because this is, the concentration, and then I increase it, yeah, to 10 particles, what we're saying in this case, we now have a more chance of particles, the frequency of collision will increase, and so the rate of reaction will also increase. Now, for this column, it's rate of reaction 1 over t, yeah? And so 1 over time. So 1 divide, and let me not use that word because, we have, it's a little math issue. So it's 1 divided by the time. So let me just put it right here. So it's 1 over 59. But before I start, let me read what is required because sometimes CXC asks you to use a certain amount of decimal place. So let's go. It says complete the table by calculating the rate of reaction 1 over t to 3 decimal place. Same thing I was saying, right? Places. So if you put it to 2, 1, you will lose mark because they're specific, guys. Once they are specific, follow the instruction. And I know sometimes, like maybe what we have just done, we just jump and start putting numbers. But please read the questions and what is required of you before you actually start to answer. Using the axis provided in figure 2 on page 7, plot a graph of rate of reaction, yeah, versus concentration. And we know, and again, if you're a physics student, if you're a bio student, if you're a chemistry student, once you have the first variable versus the second variable, the first variable goes on the, so when them say something versus something, the first something goes on which axis?
the y-axis.
So the y-axis. And the second one will go on the x-axis. So moving into the exam, right away we know that when we go down to plot this information on the graph or the grid provided, the rate of reaction would have been placed on the y-axis while the concentration would have been placed on the x-axis. Yeah? The next thing, we're required to draw the line of best fit through the points. So help me out now. Help me out now. Remember, you need a calculator, no phone. Stop doing papers with your phone as the calculator. Start practicing by now because you're not going to have that phone in the exam. If you don't have a calculator, purchase one so that you can actually get familiar with how to do your basic calculation. Even sometimes as something simple as a calculator, throw off students in an exam. So let's get those calculators up and running. So 1 divided by 59 gives us, And I know persons might have started working them out.
0.017.
So says everyone.
Yes, sir.
1 divided by 42.
0.024.
So says everyone.
Yes, sir.
1 divided by, what's this? 31.
0.032.
1 divided by 25.
0.040.
0.014.
No, 40.
4.
Yes, sir. 40.
Is there anybody who is not following what is happening? Everybody is okay?
Yes, sir.
So the 1 divided by 21.
0.048.
All right. So we would have um, captured our rate of reaction 1 over t. And remember, again, 3 decimal places. That is very critical in us, doing our 1 over t, our rate. Now, just ensure that you have, and even the exam you can do this as well. If you notice, the table is on a different page than the graph, and you are going to be given a booklet. And so what you can do quickly, note the 2 points that you're going to be jotting down, or the 2 variables rather, my bad, and you can just extract that and put it on the page. Nothing wrong, you can write on the page right here. So 0.1 to 0.017. So we just scribble it right here, just using this as an example. 0.1, and we have 0.1. How much will it say? What was it again for the first rate? Then now work with me now. Then now work with me. 0.017. So even the same thing I'm talking about. The going back and forth, right? To look at it and get back and look at it and get back. Remember, we want to maximize power time. So we can just scribble them down quickly, and then you have them to just look across to plot. Not true. So you can remind me of them.
0.024.
No, what was the concentration at that time?
0.15.
So 0.024.
0.24.
Next one.
The concentration is 0.20,
Mm-hmm.
and it's 0.032.
Mm-hmm.
And the next one is 0.25, and it's 0.040. And the next one is 0.30. There's 0.048.
Alright. So we have our little information right here, so we can work with. And the thing about this, let me probably bring this down a little bit. So we have the rate, and then we have our concentration. This not work out for me now, because I'm going to write it up there so I'm not see it. Anyway, so 0.01 to 0.017. Right? Yeah. So on this axis, watch me now. So it is 0.05 divided by 10. Not true? Because we want to find out how much each of these little strokes represent. So what is this going across? Which is what? Which is? I'm just showing you a quick way to deal with the points on the graph, or you can get to the points on a graph. So what we can do, so the first, it is, we're going up 2 centimeters to 0.05, right? So we're dividing that. So we want to find what each of these strokes, each right here. So these are the strokes. We want to find out what they represent. So we're dividing because there are 10 of them before we reach to get to that 0.05. And so if we divide that by 10, we would find out how much. And we know from our primary school days that if we're dividing by 10 or 100, all we need to do is to, move the decimal places, in this case, one place to the left. Not true?
Yes,
So our answer should be 0.05, 0.005. So each of these, yeah? Yeah?
sir.
So,
Yes, sir.
so again, I want to be able to just be capturing the points. So what I can do is to find what each of these strokes represent. So based on the fact that within this context of 2 centimeters, we have 10 strokes getting to that 0.05. So we divide that by 10. So each of these strokes is 0.005. Now the point that you want to find, we want to find 0.017. Not true? So 0.017, yeah? And answer me. Work that out and tell me how much you get. I was doing the wrong side, guys. I just, when I look back up. So it's right here. The rate of reaction would have been on the y-axis. So it would have been here. So it's really 10 divided by point 0.005 divided by 10. So the answer would have been 0.0005. So do that for me instead. So instead of this axis, I was looking, and again, pick up on my mistake, my bad. We were on the rate. So the rate was placed on the x, as we know. So this is actually for the concentration. So what is 0.017 divided by 0.0005?
34.
34. So says everyone.
Yes, sir.
So again, what I am doing, making it very easy. So what I know is that I'm counting 34 of these strokes. We already know that there are 10. So 10, 20, 30. So that would be right here. So 34 would be right here. And so it brings us directly, right, to the point, making it much easier. And the first one would have been point 1, right? Yeah?
Yes, sir.
All right. So again, sorry about the mishap in terms of the axis that I was looking at. So we're on the y-axis. So all we did was since it is from the 0 to the 2 centimeters to 0.005, we can divide that by 10 to find out how much each of these strokes represent. So them stroke here really represent 0.0005. Now that we know that, we just divide each of the points that we want to find. So if I want to find 0.024, so 0.024, I divide by 0.0005, and that will give me how many strokes? How many strokes is that?
48.
All right. So that's 48, and we're going to 1.5. So 48, sorry, 0.15. So 48. So we know 10, 20, 30, 40. So 48 is right here. Yeah. So again, what we would have done, so whenever you get and this is something maybe physics students would know, once you do physics, sometimes we're better able to deal with graphs because it really requires you to do a lot of graphs. But if you're not, again, if you want to find any point, once you find what one stroke represents on either of the axes, to get to that point, you would have divided the point that you want to find by what each of those strokes represent. You get a number. That number tells you how much strokes you need to count to get to that point. So you don't have to stress yourself. So we can get to the points quick. So all we need to do, 0.032 at the next one. Yeah.
Yes, sir.
And we divide that by 0.0005, and we're going to get a number.
I got 64.
So that number now tells me how much I need to count on my y-axis to get to the point of 0.032. So I need to count 64. So again, we already know this is in 10. So 10, 20, 30, 40, 50, 60, and we say 64. And which point is this at? Point 2, concentration. What's the concentration? How are them there? What's the concentration? They no one help me now. So let me look back myself. How them not hear me? You guys not hear me? You not hear me? Hello? So what's the next one? Point 040.
Sure, I got 80.
So again, run into 80. So we remember, so this was 60, so 70, 80, right? And we're going to 0.25. So we say 70, 80. And this one, this one even proves that, you know, our method work. Cause see it here, we're trying to, the 0.040 is actually on our graph, right? We could have really look, but just to prove the point that, you know, the method works. So we brought it to tell us that we need to get to 80, and we got to 80, and that's right where we need to be. Yeah. The next one is 0.48. So 0.048 divided by 0.0005. What's the answer we get?
96.
96. And again, this is 80, so this is 90, so 96 is right here. And we're going across to 3. So that is somewhere right here. And again, we're supposed to draw the best fit line. Bear in mind, I'm on the computer. You would have your ruler. Yeah. And so, any questions about this part of it?
No, sir.
So again, we have to learn that little concept of how to find the points if you're having problems, because not all of the graphs that are presented, you can just look at it especially if they give you in decimal places. It's a little bit of more challenge than the regular whole numbers. You just look. So usually though, CXC would have given you back in the day, they would have just given you the grid and you would have to determine your scale. So they're even making it easier. They labeled the scale and they label your axis and they gave you your, so you can't make any mistake. Because even when I was using this, then I recognized that, hey, this has a rate of reaction. So I quickly adjust. So it shouldn't be that difficult in these times in terms of your exam. When we were doing the exam like this, they not give none of them information. I just a grid I get. And you have to basically sit down and derive your scale. So hopefully that was beneficial. Yeah. So we're moving on. It says using your graph, describe the relationship between the rate of reaction and the concentration of the hydrogen peroxide. I know this might be a little bit small. Let me go back. So anybody wants to describe that? So this is key. What did we say in terms of the
Sir, is it directly proportional? Something.
um, for the physics students, they would know if you're saying directly, it's if it's the same amount. For to use that directly proportional term, you have to be going up by the same amount, right? But I don't want you as a student to do that. We want to hear you describe it. What does directly proportional even mean? So break it down.
Sir, as the rate of reaction increases, the concentration also increases.
And I want you to put it the other way. Just rephrase it the other way because we were changing the concentration. So speak on the point of view from the concentration.
As the concentration increases, the rate of reaction also increases.
Beautiful. And isn't that so? And we saw that happen because I didn't want you to put it that way where you said the rate increases, which is true, but really and truly, we want to make it a little bit practical because what we were actually doing is to change the concentration. So we were modifying that concentration. Not true, guys? It says determine the concentration of the hydrogen peroxide given that the rate of reaction is 0.045. So we have to use our graph for this to get the answer for this. This is 0.045. Yeah? So you take a ruler, and again, sorry, and then we go down. Ah, straight down. We can't draw a straight line. Don't judge me. So what is the concentration?
Zero 0.275.
All right. So says everyone.
Yes, sir.
And we saw how we got that. So you're using the, and there is, what was the value again? Sorry. 0.275.
Yes, sir.
All right. So we were using, and this is the concentration. So we know this is moles per dm cube. We using, when you do your line, and CXC knows that you might be out, so a point one to a point one difference up or down, and so they use that to determine. So even if you get something a little bit off, they're not going to penalize you.
Wait,
Calculate.
sir. Can you just go back up, please, for the line?
Here.
Yes, sir.
No bother
Okay,
watch.
thank you.
No bother watch me outer sync line. But you would have your again, and I can't stress it anymore. Do not go to the exam without the material. You know you need a pencil, you know you need a ruler. Because even in mock exams and try weekly and monthly exam, I see students who are physics, chemistry students going to exam, them now no maths, yeah, going to maths, maybe you are not those two type of students. But we go into maths exam, we not a calculator, we not a ruler. Those things are needed. So have your little kit. When I was going to school, and I like to give my little feedback as well along that line. One of the things that I would have done is to ensure that I have my little exam kit. So my rule and them something that me purchase them. Me not see students with geometry set anymore. Right? So things like that you may need these things. Right? Something simple as drawing the your compass can be used to draw proper nice circles if you are asked to do the atomic structure or the electronic configuration using the board diagram and all of that. You can have nice circles, being drawn. So you get the tools. The next question says calculate the mass of hydrogen peroxide present in the concentration identified in E2. And they said that the molar mass. Again, guys, if CXE gives you this, and when you finish, you don't use this, then something is wrong because there's a reason why they're giving you it. So again, I know that when I see this as a student, what is this really saying to me? I like to look at it as 0.275 moles is in 1000 centimeter cube. Yeah? That's what it means. So we want to convert this to mass. What type of, and we think about the relationship between moles and mass. And I always tell students, yeah, moles is the central. We have our mass, we have our volume, we have our particles. Yeah? They could have brought in moles here. They could have talked about volume of gas. Because remember, we we are dealing with the decomposition and we're getting oxygen, and we're getting what? What do we get?
Water.
And we're getting water. So they could have asked you that question, and so your head have to be on your body, and you're working. So we are at moles, and we want to get to mass. We know that 1 mole of this will be equal to 34.0 grams. But I did not have 1 mole. So this is my conversion factor that I'm going to be utilizing. For students who might be new to me, I don't go the cross multiplying route. Forgive me. If you want to go that route, fine. But usually when I do that, and I used to do it before, students still keep on asking me, sir, do I divide or do I multiply? So here's what I do. So what was given? In this sense, we have, this is what we considered as what is being provided to us. We know that we have our conversion factor. We are going to be creating a fraction. A fraction has a denominator and it also has a numerator. So I'm going to be multiplying this as a fraction, and I just say to students, whatever unit is here, that is what goes to the denominator. And I know persons would have said, oh, 1 mole equal 34.01 grams. So 2.25 moles will equal to X grams. Yeah, it's the same thing, but again, it eliminates persons, students asking me, "Oh, sir, if you divide, I hate that." And so some simple mistake with this. All we need to remember, since we have moles as that, then moles goes as the denominator. Any unit that you have here goes to that denominator. And so technically, right away, you know that you're supposed to multiply. Yeah, you can't make the mistake. Again, when I do it like this, I see another issue coming up. Issue in the sense that we're not able to interpret what this is saying. So this is saying 0.275 times 34.01. And then you divide that by, it's just that the number right here could have been 3, could have been 6, but in this case it is 1. Yeah, and we know any number divided by 1 is the same number. So technically, we're just multiplying 0.275 by 34.01. And so what do we get? What them there? Anybody?
So I got 9.21671.
You said 9.
Wait, sir, there's a mistake. 9.35275.
And you don't see that to a negative value?
No, sir.
Is that gap? Do I check again? Because if 1 mole, wait, 9 you said,
Yes, sir.
in terms of grams. So 9 point,
35275.
all right, grams. And remember, since we're calculate the mass, so this would have been the mass that is in it. So if 1 mole would have been weighing 0.01 grams, then 0.275 moles would be weighing 9.35275 grams. Yeah? If they had asked you what's the mass concentration, then you would have just, and you can even shorten this to 0.35 grams per dm cube. But they ask you what is the mass. So they never said mass concentration. So bear that in mind. So if it was mass concentration, we would have to give in the unit of grams per dm cube. But since they ask you only for the mass, we just represent it. Everybody good with this?
Yes, sir.
Sorry.
All right. The interesting part. 3 marks. Write a balanced chemical equation including state symbols to show the decomposition of hydrogen peroxide. So we know hydrogen peroxide is breaking down into what? Oxygen is one of the.
Diatomic.
So say you're with that equation, are still not so versed on balancing chemical equation, even something maybe as I wouldn't say I would say fairly like intermediate balancing we have right here. It's nothing really complex, but what I would tell students to do if you're in a if you're in any issues, do the inventory. This is not something that CXC needs to see. You can just have on a piece of paper and you do it. So how many hydrogens on this side? 2. How many hydrogens on this side? 2. Oxygen on this side? 2. Oxygen on this side? Oxygen on this side? Them not work together. And them a try balance it.
So the three oxygens on the other side.
Alright. So since as the hydrogens are already balanced, we move to the oxygen. So we would have started by getting it to an even number, which is 4. So we want to get this to 4. So how do we get this to 4? So since we
Add
have 2 here, remember when we're balancing, we can only add coefficient. If I put a 2 here, that only increases it to 5, because I know I'm going to be saying 2 times 2, and we still have a 1 over here, which is 5. But if I put the 2 here, it's 2 times the 1, which gives me 2 plus 2, which gives me 4. But remember, it will also affect your hydrogen. So 2 times this 2 gives us 4. Now we want to get these to 4, so we put a 2. So 2 times 2, 4. 2 times 2, 4. And so this would have been our balanced chemical equation. And so we earned our 3 marks putting in the state symbols. All right. Yeah. They not pay me no mind. Bringing these graph would have been solubility, easy to take into consideration a graph, heating and cooling curve, another way of getting in graph, and of course rate of reaction. Those are three areas. Yeah. So question 2 says, at atmospheric pressure, water exists in three states of matter, while carbon dioxide exists in only two states. List the three states of matter in which water can exist. And I want to mark that. Honestly, like this, I really would want to, I guess if you don't list any of the three states, because you don't get half mark in CXC. So what are the three states?
Liquid, gas, and solid.
I'm just gonna write it like how me say it. And again, the 1 mark question them rough. Because once you give that desired answer, as I said before, we are not getting any half marks. So sometimes our teachers, even me as a teacher, we say, give me a half mark or give her a half mark. But when you reach to this stage, you're not seeing any half mark, you're not getting that half mark. So please, as best as possible, ensure that you're thorough in your explanation, look at the marks that are needed, and ensure that you speak about what is required. Describe the energy of the particles in each of the three states listed. So you started with liquid. So you're going to be talking about the energy of the particles in a liquid. You have gas. You're going to talk about the energy of the particles in gas. And you have solid. You're going to be talking about the energy. And I just wanted to highlight this to show you how you would have acquired the 3 marks. So for each energy that you describe at the different state, that's how you get that 1 mark. So if you don't describe it for any of the states, then you're losing out on that mark. Cool? Come like me here by myself. How are them there?
Yes, sir.
So how would you describe the energy of the particles in a liquid?
Sure, they have just enough energy to slip over each other. That's it.
So they have enough um and what I say to students, when you come on to this energy, you have to, well, when you come on to this part of it, you have to be careful how you go about explaining, because sometimes what we're explaining is maybe the movement of the particle. But for this, I tell students to compare gas and liquid. So you compare the liquid with the gas and the solid. So it would have possessed more kinetic energy than those particles in a solid, but less kinetic energy than those in a gas. Not true? Because that sliding apart, that sliding will basically speak to the arrangement, right? Or movement of the particles. So if you want to mention it, fine, but you have to talk about kinetic energy. We have to hear about the energy that the particles have. So comparing it to solid, it has more, the particles will have more kinetic energy, right? And Miss mentioned that they would have been able to slide past each other. What would you say about gas then if you use that? We're at gas.
They are free.
They what?
They free.
And again, we want to hear about the energy.
So they have like the least amount of energy out of the three states.
Gas?
Because them under RHP, so they move freely. So
Yeah, but we're saying, remember, energy in this case, we're talking about the kinetic energy. So whatever you mention, we want to, this is the main focus, the energy of the particles, not how they move. I know that because you're saying so again, why is it that they're moving freely? Because they have a high amount of kinetic energy. So that mention of high kinetic energy is what the markers are looking for, not the fact that they're moving freely. So yes, we know they move freely, but you still haven't mentioned anything about the energy that the particles possess. We are describing the energy. And so sometimes we go in the exams and we're saying that, hey, yes, sir, may I answer the question? Yes, it is true. Gas particles move freely in any direction. But that's not what the question is asking you about. It's asking you about to describe the energy. So the energy that they have is that they have high kinetic energy. And if you want to add the fact that because of that they move freely in any direction, fine. Yeah? Yeah? And again, may not do it for bash you. I just trying to ensure that you acquire a lot of the things that we're seeing is how we interpret the question and provide our answer. It's not what you said is not incorrect, but it's not fully answering the question. So how would we describe the energy of the particles in a solid? If you come and tell me that the particles in a solid vibrate, you're not talking about the energy.
sir, them have low kinetic energy.
Wonderful. And so they vibrate if you want to add that in a fixed position. Yeah? Closely packed if you want to talk about that. But those things are different properties if you look at it. If you look at the tables that they provide, arrangement of the particles, that's when you talk about the closely packed. Yeah? Movement of particles, that's when we talk about vibration. So if you add it, we still want to hear something specific about the energy. Yeah? Movement. Yeah? Tell them about the energy. Nobody, we all right? It says, name the process which occurs when carbon dioxide changes from one state to another.
Sir, sublimation.
Wonderful. Nacho, what is sublimation?
The process when a gas moves from to a solid.
You sure?
So move from solid to gas.
So solid to gas. Yeah? The other way would have been deposition.
Oh,
All right. Describe how the arrangement of the carbon dioxide particles changes as carbon dioxide undergoes the process named. And again, you see what they want you to talk about. Again, we're seeing this word describe. What they want to talk about?
the particles,
What about the particles?
the arrangement of
The
the
Arrangement.
arrangement. So we don't want to come and talk about, oh, the particles then would have a high energy. Because again, that would have been talking about, or that is now linking to the kinetic energy that we would have mentioned up earlier. So if you notice what they're doing, they're checking, they're really testing your knowledge to see if you know about. You remember that table that teachers normally give to you? We give you the different properties and we compare it, how the volume is, how the shape, the arrangement, all of that. So that is what they're testing you on. So the first thing they test you is to see if you know the process. So again, you should know that it's moving from a solid to a gas without passing through the liquid state. Yeah? So what they want you to tell them? How are the particles of the carbon dioxide are in the solid, and how would you describe that?
Sir, they're tightly packed.
Wonderful. So they are tightly packed, and how would you describe them when they're in a gas?
Sir, they move freely.
Now, again, you see what you did? You start to talk about movement. So how are they arranged?
Sir, they're widely spreading.
So they have there are a lot of spaces between the particles. Yeah? So they're not close together like that of solid. Not Joe. And we would have earned our 2 marks. So 1 mark to talk about how they are in the solid, 1 mark to talk about how they are in the gas. I jump over the I think some Nasia. It's Nasia.
yes, sir.
Good morning.
Morning.
You're okay?
Yes, sir.
Following?
Yes, sir.
Great. Miss Zara. I say go.
Yes, sir.
We're good.
Yes, sir.
Miss Lane, our street.
Yes, sir.
All right, to understand what's happening. May I hear Miss Samuel some morning? I just double checking, you know, um, because I want to ensure everybody. Miss Query, I know that you've been responding, so everybody is actively involved. It says using appropriate diagrams, illustrate the lattice structure of sodium chloride. Sodium chloride. What's the formula for sodium chloride?
NaCl.
Wonderful. And we said it's and we have a giant molecular structure, diamond. Diamond is an allotrope of carbon. Not true. Who is the
Mercury.
who is the counterpart to diamond?
Graphite.
Wonderful. And we said that's a sodium chloride. Normally, I give students this little. I used to do it a lot when I was younger with the squares. Now, here's something that I see students do. CXC provides this space. You see the space? And so for persons who even have the booklet, I don't want to, but if you have the, and you come scribble the little thing, see them here? Just so them scribble the thing. Maximize on the space that they provide. Again, this is where your ruler and your pencil will be needed. So don't think that, hey, I have to, you know, always, we might not need the ruler. You have cases where you need to draw. So if we're using dots to represent the chlorine ion, and then we're using that to represent the sodium ion, then it's looking something like that. And so we know that we have a situation where each, ion is bonded to a cation, and the anion is forming that bond to give you that crystal. So at no point you have the two same ions bonding. Yeah. So in this crystal, one of the things that we would have known is that the concept of the ions, they are in fixed position. And that's one of the reasons why solid sodium chloride is not capable to be utilized in your electrolysis. So if you're going to be using the electrolysis of sodium chloride, or if you're going to be talking about this transmitting electric current, it cannot do it in the solid state because these ions are held in a fixed position. In order for them to transmit electric current, they need to be mobile. And so, popular question as well, asked by CXC, they will give you scenarios. So you should know the only time that this will transmit electric current is if it is molten or aqueous, where aqueous is when it is dissolved in water. Molten is when we melt it, and we know the bonds are very strong, so we have to melt it at high degrees Celsius. So even if you put salt in your oven and turn on your oven, it will not melt. It's just going to remain because the temperature is not high enough. Energy is not high enough to break the bonds. Yeah? So this is what they're looking for, highlighting the different ions, stating how they're bonding. Yeah? Now with diamond, we say each carbon is technically bonded to 4 other carbons. So really and truly, what we normally do is to highlight the carbon in question. So each carbon is really bonded to 4 other carbons. And that's one of the reasons why diamond is not capable of transmitting electric current like its counterpart graphite. So we have a situation where each carbon is covalently bonded to 4 other carbons, and so there's no free electrons, no delocalized electrons, no mobile electrons, and so the diamond is not capable of transmitting electric current, but graphite can. It's one of the strongest substances known to man as well, and so we use diamond in the drill. We use it in the bits of drill that we're digging into the earth for oil. They never say them find oil in Jamaica. How is that going? Around the sea. We are, because of the strength of this, and there's a lot of little videos on YouTube that you can use, people using hammer to hit the diamond and the hammer actually a break, you know, instead of the diamond, the hammer actually a chip instead of the diamond breaking. So it's very strong. Practice to draw the diagram of these three, the diamond, the graphite, and the sodium chloride. Sometimes they do come back under bonding and structure. Yeah? Yeah? So C says, in solution, two metals A and B form A plus and B2 plus ions respectively. Metal A displaces Fe from a solution containing Fe2 plus ions, but metal B does not. Right? So in that case, what would you say if you were asked about the reactivity? Or would you arrange these in terms of reactivity? In terms of metal A, B, and the iron, how would you arrange them? Anybody? So if you notice, okay, go ahead.
Sarah's gonna say A, then the iron, then B.
Beautiful. So in terms of reactivity, whatever the metal A or B is, we would have recognized that A is able to displace. And so we call that single displacement reaction, where a more reactive metal is capable of displacing a least reactive metal. And that's what we saw when they spoke about A reacting with the solution of iron that has iron too. Not true? True? Then answer me. While B wouldn't be able to replace or displace iron too, and that would have been because it is not as reactive as iron. So we know it must have been below iron. So here's the thing. We are asked to write a balance equation to show. So we know A would have been a solid, not true? And it is reacting with iron 2 plus, meaning aqueous. meaning that this iron 2 would have been bonded to a anion. So it could have been a nitrate, oxide, something along that line. But we don't know. We're not really interested in that. We don't have to show that. But what we do know is that since as this is going to be taking the place, then the A is going to become the aqueous. Not true. Because whatever the iron was bonded to, what happens in a single displacement reaction? And we want to go back a little further. The iron, which is a metal, would have been given 2 electrons. You see that? Because it's a 2 plus. It would have given 2 electrons to whatever anion that is there. Yeah? So it would have been given those 2 electrons. What happens when this comes along? When A is more reactive, it is saying, hey, you don't need the electrons from the iron. Take my electrons instead and get rid of that iron. So it kicks off the iron. Hey, iron, take back your 2 electrons that you were given. I will take this 1 electron, because remember, the fact that it is A plus, we know, and that you're getting your CXC exam, not true, A plus. We know that that means that there's 1 electron. So you have a lot of things that as a chemistry student you should be deducing. There's 1 electron on the outer shell. A must be a metal in group 1. Not true? Yeah? Then now answer me. So
Yes, sir.
when the iron gets back the electron, it is becoming going back to the atom state. So this is your balance equation. Yeah? Yeah?
Yes, sir.
Any questions?
So,
We have a little bit of minutes remaining. I know we started late, but even with that, I know persons have other engagements, whether to go to church or maybe even another class. So figure 3 shows the fully displayed structures of 3 compounds, A, B, and C, which are from different homologous series. And homologous series, anybody can tell me, well, let's skip that. I'm going to be talking about each of these, yeah? So we are recognizing that in this compound, we're not seeing any double bond, we're not seeing any hydroxyl group, we're not seeing any acid functional group, and so we're only seeing carbon to carbon single bonds. So which homologous series does this belong to? I know the questions are there, but I'm just using this as a teaching method as well. So which homologous series does this belong to? There's only one homologous series that only has single to single carbon bonds, and those are referred to as the alkanes. Now, we know that an organic compound has 2 parts. It has the prefix and it has the suffix. In this case, the suffix that it's going to end with is "ane" because it's an alkane, and we note that by looking on the structure. And we said these are the structural formulas, which shows a two diagrammatic representation of a compound. So it shows the bonding. As well, if you're new to organic, these strokes are really showing you the covalent bonding. Remember when you were asked to show covalent bonding back then in atomic structure? So we know that there are two electrons present in the single covalent bond, and these electrons are being shared. Yeah? Now, 1, 2, 3, 4, 5. The fact that we have 5 carbons, the prefix for 5 is pent. So we have some prefix that we use. So for 5, it's pent. For 4 is but. For 3 is prop. For 2 is eth. For 1 is meth. For 6 is hex. We need to know those, right? All right. And so we end with ane. So this is also pentane. And so the formula is C5H12. And I can tell you that it's 12 even before counting because every alkane has this general formula. So the general formula, where N is the number of carbons. So if I want to know the number of hydrogens, it is 2 times 5 plus 2, which is 12. So just a little information about this. We want to talk a little bit again. You see, there is only hydrogen and carbons. So we refer to this as a hydrocarbon. Yeah? So this is a hydrocarbon because there's only hydrogen and carbon atoms present. We're jumping over the fact that we're seeing this. This denotes a acid. This is a functional group of an acid. Remember when you were looking at ionic compounds, and one of the anions that you would have known is this, if you can recall. You remember this anion? Anybody knows what this anion is? This anion?
So is that? I don't know. It's not. Look, remember.
So we call this anion, and our Messi is trying to remember, the ethanoate.
Gosh,
So the ethanoate ion. And it's coming from the fact that we have ethanoic acid. Yeah? So remember, and this is where we spoke about the hydrogen being at the back of this compound. Very important. So usually the cation gets preference, yeah? But when you're doing it for these organic compounds, they are given preference, meaning they are written first. If you have a metal, the metal will come after. So the hydrogen, if you notice in all the other cases of the acids that we know, which are inorganic acid, and so sulfuric acid, hydrochloric acid, nitric acid, all of them, the hydrogen comes in front at the prefix or before, right? Before the anion. But this anion, because it is a organic, it gets preference. So the hydrogen is written at the last. Now, why was I really mentioning all of this? When we see this, This is also a representation of it. This is it. So whenever we see this being drawn, normally what we do is to draw this at the end of the organic compound. So once you see this, guys, this is the functional group for an acid. So it's a representation of being this. Cool? So again, if you see this, don't get confused and say, what is this? This is it when we write it. So when we're writing it, if you notice ethanoic acid, it would be written like that without this right here. Let me get rid of that. So this would have been the formula for ethanoic acid. So this portion, the functional group, it is what denotes the organic compound. That is the part that is going to take part in any reaction. We're also seeing another we're seeing another functional group here. The functional group for an alkane would have been the carbon to carbon single bond. So anywhere the reaction can actually take place. Yeah. So these are the functional groups. Look at them keenly. We have the alkenes missing. And by mentioning the alkene, let me also eliminate that fact that some students may have thought that this is an alkene because they're seeing a double bond. Remember, the double bond must be between two carbons. So even though this is actually a double bond, but it's between an oxygen and a carbon, it cannot denote what a alkene is. So if it's supposed to be an alkene, the double bond would have been present between two carbon atoms. I just want to ensure we clear that up. So in this case, we have those three compounds. So let's talk about the name of this one. We're seeing three carbons, and again, what you would have done is use the prefix. The prefix is prop, and so this is, and then we end with anoic acid. So that would have been propanoic acid. I know I haven't gone into the details of the questions yet. So I was just, working with the time. I went over the time a little bit. So let's jump to this. We're seeing the hydroxyl group. Once we see this denotes the functional group of an alcohol, right? Functional group of an alcohol. And again, when we're dealing with the alcohol, we end with anol. So we are seeing two carbons, and so the prefix for two is eth. And so this would have been ethanol. And we are familiar with that in terms of, in our everyday when we talk about ethanol. Yeah? So this is just a brief introductory in terms of running through. May not even look at the questions as yet in terms of what they're asking, but just to kind of introduce you to some amount of level of organic chemistry. Yeah. So really when you get that as a student, all of that information supposed to flow in your head because you're ready to answer. So it says state the homologous series to which A and B belong. So A would have been belonging to the alkanes, and we know why. B would have been belonging to we call them in some books, you'll see the term carboxylic acids or alkanoic acids, organic acids. Yeah? So those are the homologous series. The homologous series are denoted by their functional group. So everybody in a homologous series have the same functional group. So once I'm an acid, I'm going to have this functional group. Once I'm an alkane, I will have those only single to single bond. Once I'm an alcohol, I'll have that hydroxyl group. And so this would have brought me to the end of this class we're going to pick up next week and continue working the paper. So I hope it was beneficial. This is the part where you say yes, sir, but you're not paying me no mind.
Yes.
Fair.
So that is basically it. Enjoy the rest of the weekend of what it is.
So you can save the paper and send it to us, please.
I can, but at the same time, remember, I may not finish it. But yeah, maybe when we complete it, I probably can save this part.
Okay.
All right. So that brings us to a part one of this paper. So if you require the past papers, you can contact us and we will get it to you. All right. So again, thanks for choosing making it buckle down tutoring services. You know, your future is our priority. This is Mr. Thomas. That's it.